There's one question about a problem from the previous section, and that's 7.1, page 328, number 4. And let's see, I think it's y as f of x is 1 over, see, x minus 1, if I remember right there. And they prescribe the domain for you. They say x is strictly greater than 1. Now, we all know x shouldn't be equal to 1. That's not a valid arithmetic expression. But in fact, they're making the domain even littler. And I told you about an example yesterday when I assigned alpha numbers to midshipmen. Rather than assign them to an entire brigade, I might assign them to a class or a company or something of that nature. So they've actually made the domain smaller by making this requirement right here. Now, the problem gives you the inverse. Let's go ahead and actually try to do what we can just from what we see here. And that is, if you take reciprocals of both sides, you get this. You can add 1 to both sides, solve for x. And if you wish, you could write that as x equals 1 plus y over y. And this would be my candidate for the inverse function. I've also suggested you draw a little bit of a picture, perhaps, see what's going on. I think over here it's not so bad. Again, if you look at y as a function of x up here, I think you'll find that there's a vertical asymptote at x equals plus 1, and that this curve looks something like this. If you sketch a few points, you might satisfy yourself as that being the case. And then I said that the inverse function you could get by simply flipping this over a 45-degree line if you want to graph that. But what this does point out is a couple of things. For example, as we've said, x can only be greater than 1. By the way, I've thrown away this part over here. This is when x is less than 1. That's not a part of the problem anymore. And you can look at this and say, well, obviously the range for this original function would be y's that are greater than 0 and up to plus infinity. So it looks like over here y could be any positive value. Now it's important to establish domain and range up here because, of course, for the inverse function it's just reversed. This would be the domain for the inverse function, and its range values, x over here, would be those that are greater than 1. Well, I guess to finish up the problem, one should take g of f of x and f of g of y to make sure that they are inverses, but I don't think you'll run into any trouble here. I think the hang-up perhaps was this very fact over here, that the domain was a little bit littler than perhaps you anticipated. But let me give you some more in terms of graphics now that we've done some more in this class. If you start out with x, this gets you over to f of x, which is y. And if you turn around and go the other way, starting with this y, if our algebra is correct, that should get you back to x again. And that's all you're doing when you're checking whether functions are inverses of one another. X followed by f followed by g should get you back to the same number you started with. Okay. Well, I don't know what to do. I think in this particular case it should be easy to show that those relationships are true. Okay. And well, I'll leave it to you to try that out. But here is, I think, what the inverse should be, and in particular what its domain is. Well, let's push on then. Nobody seems want me to keep working on that one. At least I'd like to work on something else. And the reason I want to work on something else is because it's kind of interesting to me, and that's the old problem of money. We all have that problem. And what I want to propose is an example which gets us into this topic and maybe explains why the logarithm we're going to investigate is in fact a natural logarithm, in the sense that it arises naturally in some problems. Later on we'll talk about examples from chemistry and physics, electrical circuits, I think, perhaps, radioactive decay, stuff like that. I like to talk about money because it's something everybody understands. At least You're supposed to understand it these days. My question is, if you invest $1,000 at 8.5% compounded continuously, what do you receive at the end of a year? And we'll assume what's typical today, you put your money in and it's instantaneously drawing interest, compounded continuously, 8.5%, and then a year from now, what do you get? Well, most people don't know the answer, because most of the times when you look at the ads or you talk to the bank person, they'll say, this is what your actual rate is, and the yield is such and such. So supposedly they've computed it for you, and you lose interest as to where that such and such came from. What is the actual yield rate? It's actually more than 8.5%. See, if you just did simple interest, that is, at the end of the year you got 8.5%, you'd wind up with $1,085. In other words, you've increased your nest egg there by a total of $85. But compounding quarterly gives you a little bit more. You can figure that out. And if you do it every month, as some banks used to do, I guess some still do, or every day, you get a little bit more. And if you do it every instant of every day of the entire year, you're supposed to get the best possible situation. And that's what compounding continuously is supposed to at least bring to mind. But really, what does it mean? Where do they come up with those numbers? What do they get for that yield, and how do they get it? That's the question today. So let's let M of t be the amount of money you have at the time t, which will be measured in years. I guess we'll talk about fractions, but it's kind of irrelevant. This continuous compounding I'm going to translate it for you. I'll write it down and see if you can agree with it anyway. I think the mathematical model that you'd use for continuous compounding would be this one. dm dt is 0.085 m. We're going to look at this kind of an equation lots in a couple more sections, but right now it's probably startling and not what you imagined your bank was doing. But nonetheless, this is exactly what they're supposed to be doing. And what it says is that your rate of growth, that's the thing on the left-hand side. Now, I've got to assume money is continuous, but that's okay. Don't worry about that. Your rate of growth at any instant, it's like a velocity problem. How fast is your money increasing? That rate of growth is 8.5% of the amount present. That's what continuous compounding means. Or maybe I should write it a different way, and I don't know which one will appeal to you more, but let's do it this way. Okay, the rate of growth divided by the amount of money present is 8.5%. That's supposed to be what 8.5% means. The rate of growth over the amount that you have is 8.5%. Now, if you think about it, that's really what simple interest was kind of like. We said that the amount that the quantity grows in a year, if it were just simple interest, would be 8.5% of the amount present at the end of the year. In other words, $85 if you just do it once. And so I've translated that mostly into a calculus type problem. Rate of growth is at every instant 8.5% of the amount present. It's always growing at 8.5%. Now, it turns out that I really like to work with this part right here, and I do want to use this Leibniz notation. That is, I want to think of these as being differentials as opposed to a derivative like this. So what I'll do is, let's see, multiply both sides by dt. And you haven't seen this before, but you will. In fact, in differential equations, you'll be doing things like this in a couple of semesters. And now that I have it in that form, what I want to do is integrate both sides. You see the thing I hope to accomplish is to figure out what m is. That's the whole point. What is m from our model? Well, the right-hand side is no problem. That's 0.085 t plus some additive constant. But it's the left-hand side that we're stuck on, it turns out. Okay, so this is the state of the situation. I've figured out what continuous compounding is. I want to solve for m, and in a sense this is the way to do it, to separate the variables, they call it, and then by taking integrals be able to undo the differentials and get back to the function m. Once I have m, then I can answer the question by sticking in 1 for the time, 1 year. But I'm stuck. You may not realize you're stuck. Let me remind you what you do know. In fact, someone just asked a question like that not too long ago. And that is, if you integrate a power, you all know the formula, supposedly anyway, u to the n plus 1 over n plus 1 plus a constant, except in one case. And that was, obviously, n cannot be -1, because this doesn't even make any sense. And that, unfortunately, is exactly where we are over here. If you check it out, we're talking about m to the -1 dm, or, in other words, what we don't have is the reciprocal of u du. I shouldn't write it that way because it looks like an inverse function, so let me go back and change that. 1 over u du is a question mark. We don't have a formula for that. We don't have a function yet whose derivative is 1 over u. So what we have to do is manufacture it. As it turns out, there is no function, at least that we know yet, which has that derivative. And so we simply manufacture what we need. And this is what makes this section kind of strange looking. I'll try to show you, well, at least I've shown you why we have to do it, and I'll give you some highlights as to how it's done. And this seems to be right out of left field, to borrow an old phrase. That's the way we manufacture our function. L of x is this, which I want you to look at it as the following. It's the area under the 1 over t curve from t equals 1 to t equals x. In other words, I'm creating a function by calculating areas. And that's what makes this section so strange. Seems like a weird way to define a function. You're used to a lot of functions that are somewhat strange, like the sine of x. It's opposite over hypotenuse if you have the right triangle. But this one doesn't look at all natural, yet it turns out it is fairly natural, as we'll see. In terms of a picture, it would go something like this. You take the curve 1 over t, that looks like that. We saw one like that here in an earlier problem, in fact. It's a hyperbola, if you want to name the thing, but nonetheless, that's what it looks like. And this L of x you get by finding the area under this curve from 1 to x. Okay, so that area is L of x. And you can kind of see what happens here. We move x around. For example, if we increase x, L of x increases. We can put x over here on the interval from 0 to 1. Anyone have any ideas of what happens to L of x then? We're integrating from 1 to something to its left. What would that create in terms of areas? No, let's give me another, yeah, that's what I wanted to hear there. If this is my x, let's call that the orange x, I guess. Here's the blue x. If I integrate from 1 over to here, since you're going right to left, you're going to have a negative area. Could you put x over here? You might ask yourself. The answer is no. It turns out that this curve is such that you would get problems. In fact, it doesn't exist over there. I guess you'd have to switch to this other branch down here, 1 over t, and you've got problems. That's a discontinuous curve. So we have to avoid that, in fact. So what happens is we only define this for positive x. That's, in fact, the only ones we need, and it works out quite well that way. Okay, now let me tell you what is important here. Well, let's start out first by the fundamental theorem of integral calculus. I'm afraid that calls upon some memory of yours, which is perhaps a little rusty as to what that said. Let me remind you, by the fundamental theorem of integral calculus, if you define a function like this as an area function, then that derivative of cap f is little f evaluated at x. That's what the fundamental theorem said. If you take the derivative of the area function, you get the integrand with that variable stuck in. That's a rather technical result, but it's what you've used quite a bit already in order to analyze certain problems. For example, when you did volumes of revolution, you had to set up an integral and find an antiderivative. And in a sense, you're using the fundamental theorem at that point. Okay? Well, the reason I pull this out of the hat, so to speak, is if you take our function, L of x, which I've defined to be the integral from 1 to x of 1 over t dt, then this fundamental theorem says that L prime of x is, well, the function is 1 over x now when I plug that x in. And that's just what I wanted. I wanted a function whose derivative was 1 over x. For the purposes we have, that means that if I take the antiderivative of 1 over x dx, then L of x is the function that I need. It seems circular, but in effect it isn't. The reason is that we've defined L of x as an area function, which is a legitimate definition, and then shown you that it has, by the fundamental theorem, the right property that we need. Well, it's one thing to define a function, it's another to figure out what the thing looks like. Let me give you an instance of that. What if you wanted, for example, L of 2? Okay. Okay. Well, what you have to do is somehow figure out what the area is under the curve from 1 to 2. And if you figure out that area, then you've got your answer. Now, the immediate reaction is, why don't we use calculus? But then it does become circular. What you're saying is, let's find a function whose derivatives is 1 over t, and then take L of 2 minus L of 1. Well, you can't do that because you've just manufactured that function. So in other words, you can't use calculus at this point. You're trying to use calculus on a function which, in effect, hasn't even been defined yet, at least computationally. Well, the answer is that you have to use what we call numerical techniques, which says something like what you did last semester. We could use, let's say, 20 rectangular approximations, 20 inscribed rectangles, would give you a pretty good approximation to L of 2. And if you're not satisfied with that, you could use 40 or 100 or whatever. You could use something fancy like trapezoidal rule, which we didn't cover last semester. It's in the book, but It's a nice effective way to approximate area under a curve by using trapezoids. You can use Simpson's rule. In fact, most of those TI-55-2 calculators have an integral button which gives you an approximate area under a curve. You could use that to figure out L of 2. But the whole moral of the story is somehow you've got to numerically come up with this thing. You don't get to use calculus. You've got to attack area directly and use some kind of approximation to get your answer. Well, as it turns out, using one of those techniques, I happen to remember what the L of 2 is. It's 0.6932. Approximately, you can get more digits if you wish, if you work harder at it. But that's an example. So now we're almost ready to draw what this function looks like. I want to draw L of x. Okay? And we've got 1 point. Actually, we've got 2 if we step back here and think about it. Remember, if you look at the area from, let's say, 1 to 1, obviously you don't have any area, which means that L of 1 is 0. Okay, so if I stick in x equals 1, that area is 0. Everybody's supposed to know that. The area under a null curve doesn't exist. So here we are at 1, and the function looks like that. There's L of 1. And I've just told you that if you do some fancy footwork on your calculator or computer, you can come up with L of 2 pretty accurately, and you get 0.6932, approximately. And you could do the same. You could do 3 and some fractions, and the best thing to do would be to put it on a computer and let it do all the work for you, include drawing the graph. If you do that or something of that nature, what you'll find is the curve looks like that. Okay, and more about that curve later, but what I'm trying to say is, now that I define the function this way, at least I can compute its values for any x by some numerical technique, and then I've got a curve for the function. And as soon as I have a curve, I feel a little bit more confident as to really having the function in hand. Well, that's not the end of the story. That says, well, we have a function which has the right derivative, and I kind of know what it looks like, but here's the amazing part. It still amazes me. If you look at L of a times b, in other words, if in your argument you put a times b for x, you will show, as the book does, you can show, I should say probably, you can show that L of a times b is L of a plus L of b. Now you may say why. I'll tell you a little bit more before I answer that. If you deal with a quotient, it looks like that. L of a over b is L of a minus L of b. And if you deal with powers, let's say rational powers for now, L of a to the r turns out to be r L of a. See text for proof. I don't want to go through the details. It's all there. I couldn't do any better than they could. So we have a function defined. It has a certain derivative property, which we wanted. It has a certain graph, which we saw. And now we see it has these properties as well. Does anyone realize what those properties are? Logarithmic properties. We talked about them for log base 10. Log of a product is the sum of logs. And it turns out this L function has that same property, as well as these other two. It turns out that L of x is in fact just like a logarithm. And as such, we call it a logarithm, and we give it a special name. Put that in quotes, looks like a logarithm, meaning it has logarithmic properties. And we call it the natural logarithm. More about natural later. And we also give it a special name, Ln of x. Supposedly L for logarithm, N for natural logarithm of x. And that's the way you'll see it in the book. That capital L of x notation was purely for the introductory material. Now that we see that it is a logarithm, we call it a logarithm. So let me remind you of the properties that we've come up with here so far. For one, the definition, as you see it in the book, looks like this. Ln of x is this creature. It has this as its function. Forget the capital L, that was just my notation. This is the way it's going to be now, as this is its graph. It has a very important property that if you take the x derivative, you get 1 over x. That was the fundamental theorem. If you throw in the chain rule, which always comes free of charge, I'll call it CR for chain rule. If you take the derivative of the log of some function, you get 1 over that function du dx. That's the old d log u, which is 1 over u times du dx. So that's probably the best way to remember the result. And also you ought to realize that once you have a derivative property, you also have a cheap, in other words a free, integral property. Du over u is the natural log of u plus a constant. So it comes absolutely free as well. I should now go into some homework type problems, but I'm more excited about my money problems. Let me finish up with that right now. You see, the whole point of that money problem was that I got hung up at one point. Now I've gotten past that point. And it goes something like this. This is what we had. I divided both sides by m multiplied by dt. And then I integrated both sides. No problem. Now I know what the left-hand side is. It's a log. And I should have an additive constant, but I'll throw it over on the right-hand side with whatever else is supposed to come over here. Okay, now I've got log of m is 0.085 t plus c. What I want is m. That's the whole point, and then I'll have m of 1. This is actually what I'm after, is m of t. So I'm that far from an answer. 2 steps, but they're big steps. To show you what's going to happen, I need to somehow undo the log. I need an inverse function, and that's going to be the next section. And then all we do is plug in 1 to get that final answer. Before we do that, next time I'll go back and look at lots of your homework problems which involve these kinds of computations. We'll look at several of those. And really what I want to do is push on and try to get this thing solved. So we'll see you next time.